So we're first going to graph y equals 1/3 of the x. I think we even did this one already, right, in the last part. So when graphing y equals 1/3 of the x, set up your axes. You know that all of our exponential graphs so far, they all go through 0, 1. And this one, when you plug in 1, is going to go through 1, 1/3. So based on where those two points are, if you're going to connect them, the only way that you can get that swooping motion is if this one swoops down. Add our asymptote in there. At y equals 0. And we have our graph. Now that we've drawn our graph, and this is all you're going to ever need for drawing your graph, you're going to need to label your asymptote and those 2 points. So what happens to y as x increases by 1? So if I do add some more points on here, can you see that your next one is going to be 2, 1/9? And each time x increases by 1, the y value goes from 1 to 1/3 to 1/9. The next one will be 1/27. Each time x increases by 1, y is multiplied by something. And in this case, your y is multiplied by 1/3. So every time your x value goes up by 1, your y value gets multiplied by 1/3. It's probably easier to see with a number that wasn't a fraction. Like if you had y equals 2 to the x, you'd have 0, 1, 1, 2, 2, 4, 3, 8. And as x increases by 1 there, your y value gets multiplied by 2. So whatever the base of your exponential function is, in this case the base is 1/3, every time x goes up by 1, your y value is going to be multiplied by the base again. Is this function increasing or decreasing? To determine that, we always go from left to right. And you can even think of maybe what would happen to this ball as you went from left to right. Well, it would roll down and be decreasing. So for this, we can just circle that this one is decreasing. The intercepts, well, it only has a y-intercept. A y-intercept at 1. There are no x-intercepts. The equation of the asymptote, we've already labeled on our graph. The domain are our x values, and there's not an x value that you can't plug in. There's no non-permissible values, so your domain is everything. X belongs to all the real numbers. And the range, well, your y values are all bigger than 0. Not bigger than and equal to, because there's an asymptote at 0, but bigger than 0. Okay, so the questions for this are 3, 5, and 7. We are not going to do those right now. Instead, I'm going to give you another graph. So if you turn the page, you have room on 346. And I'm going to get you to review your transformations. And we're going to graph -5 times 3 to the 2x plus 4 minus 7. That's a bad looking 7. Recall from transformations, we would work from left to right. But before we even do that, one of the things that you always did in transformations, before you worked left to right, is you thought about, what was my parent graph? What graph am I going to base things on? And so we need to look at this and say, well, where's my x? My x is in an exponent. So my parent graph is going to be an exponential graph, which kind of makes sense because that's the unit that we're on. But if we look at this, we need a parent graph which is something to the power x. What do you think the base is going to be of our parent graph? What's the base in this graph? It's just a 3. So you're going to have to be able to look at this graph with all those transformations and pull out of that our parent graph is y equals 3 to the x. And since we've done a bunch of these graphs already today, by now I'm hoping you can quickly sketch this one and be able to say, I know it goes through 0, 1 and 1, 3, and I know it has an asymptote here at 0. And we can draw a very, very quick sketch of that parent graph off to the side. Because what we're going to take from that parent graph are, there's my 2 points, 0, 1, and 1, 3, and there's my asymptote at y equals 0. And now I have to figure out, where do those points go? What happens to them? Well, what would the negative 5 do if we're going from left to right? Does that affect the x values, or is it going to affect the y values? It's going to affect our y values. What are we going to do to our y values? We're going to multiply them by negative 5. That's what we're going to do algebraically. If we had to describe it in words, the negative is a vertical reflection. If you flip something vertically, which axis does it go over? Over the x-axis. And the 5 would be a vertical stretch by a factor of 5. So we've got a vertical reflection and a vertical stretch. Now, sometimes, especially it seems with exponential graphs, it's important to think that 3 to the x is my parent graph. Nobody ever gets confused with the x. You never think, oh, I should do a vertical translation x to the right or something. That makes no sense whatsoever. But nobody ever gets confused with the x because it's a variable. You never think of it as a transformation. But you will get confused with the 3 because the 3 looks like a number and you say, I'm going from left to right. I hit my negative 5. Now I hit a 3. What should I do with the 3? Nothing. It's part of your parent graph. So sometimes people highlight them, say that's part of my parent graph, that's part of my base graph. I don't have to do anything with it. Whereas before, everything that we had in transformations up till now, all the extra symbols were easy to not mix up with transformations. But now that's a big 3 that looks like a regular 3. You might want to do another vertical stretch by 3. You might be tempted to multiply the negative 5 and the 3 together and just start with negative 15. Okay? Why can't I multiply the negative 5 and the 3 together?
Because you get an ungraphable graph.
Well, but maybe the negative's out in front. Why can't I, if it wasn't a negative, why can't I multiply the 5 and the 3 together?
Because you're only applying the power to the 3.
Okay. There's an order of operations is here. Right? You remember in grade, who knows when, you learned like BEDMAS that says you do brackets, then exponents, then division, then multiplying. Well, exponents come before multiplication. And this negative 5 times a 3, that's multiplication, but the 3 has an exponent. So that exponent needs to be dealt with first before you can multiply that by that negative 5. But oh, you will be tempted. The all unit, you're going to be tempted to multiply that number in front by that base. It's going to be whether or not you can hold back on that temptation. So you're not allowed to multiply those together. So since this 3 is part of our parent function, the next thing that we run into is that 2. Is that going to be vertical or horizontal? Horizontal. So again, to help you figure out what's horizontal and what's vertical, we say that anything that's inside the function, in other words, anything that's where the x is, so in this case, in the exponent, that's going to affect things horizontally. So sometimes people like to do things like, oh, I'll put a red box around that so that I can tell, I can see that's everything in the exponent. All of that stuff is going to be horizontal. So that 2 is going to multiply our x values. What are we going to multiply x by? Do you remember how to do horizontal stretches and corrections? 1/2. Right? All of our horizontal compressions, we're multiplying by the reciprocal. And so we could call this, it's not a horizontal stretch because we're multiplying by 1/2. It's a horizontal compression. The 4 is going to move 4 units to the left. And finally, the 7 units to the down. I like that. So now that we've decoded it, we can take our points just like we did back in our first unit, 0, 1, 1, 3. We'll deal with our asymptote right at the end. And remember when we did these arrows, we did all of our stretches and compressions first. So in this one, we're going to multiply our y values by -5, our x values by 1/2, and see where they go. So multiplying x by 1/2, that'll stay 0, 0, -5. And here by 1/2 will be 1/2 and -15. And then in our second set of arrows, we did, moving from left to right, all of our translations. So we're going to go 4 to the left and 7 down. Well, that'll make this -4, -12. And we'll go to a decimal here, -3.5, -22. With our asymptote at 0, will multiplying y by anything have an effect? No, because it's at 0. Doing anything with the x on y equals 0 will have no effect. Right? So when you multiply x by something, that doesn't change y equals 0. Moving it 4 to the left, right? It's going to stay exactly where it is. But finally, the only thing that's going to change your asymptote at y equals 0 is whether things are moved up and down. Our graph has been moved 7 down, so we can go right to the end and say our asymptote is going to be at y equals -7. So once we have our points, start by graphing your asymptote, y equals -7. Add your 2 points. So we've got -4, -12. And I'm just going to estimate -3.5, -22. So I'm going to label these. And finally, we need to show the shape of the graph. So in between here, these two are connected like this. That means it needs to swoop up towards this graph. It's going to continue down on forever. Make sure you remember your arrowheads on the end of your graphs. And we have our shape of our graph. So if we think back to what we had originally, if we just think of all of our transformations, has it been reflected over the x-axis? Does our final graph look like it's been flipped down? Yes. It's a little bit sometimes hard to see the vertical stretch, but it does look a little bit steeper than it was originally. The horizontal compression is also hard to see, but does it look like it's been moved 4 to the left? Yeah. It looks like it's been shifted to the left. Does it look like it's been shifted down? Definitely. We have our asymptote moved down. So you can run through your transformations at the end and just do a check. Does it seem reasonable? Right? We can't say, oh, it looks perfect, because we're not quite sure of that. But based on where our points are and based on the final shape of our graph, we can say, yes, I think that this seems reasonable. So again,